Thanks to anyone who listens to this presentation. My name is Kim Pepin. I'm a research biologist at the National Wildlife Research Center with the Feral Swine Program. I'm going to talk about a study on optimizing bait site density for controlling feral swine with toxicants. So I'll jump right into the motivation here. So basically, there's at the National Wildlife Research Center, led by VerCauteren and Nathan Snow, there's a toxic bait under development. The product is not finalized. There's been a lot of research put into optimizing its safety and humaneness. But what we do know so far is that death occurs quickly. Most feral swine will die when they eat the bait, but a small number will survive, because of social interactions that happen at the bait site. And that in order to use this bait, there will have to be pre-baiting to, just like with traps, to attract pigs to bait sites, and then a training period for using the bait-specific box that this product will be delivered in. This box is important for excluding some common non-targets. So the questions we had is, when we have a toxicant in hand that we can use, how will we use it on the landscape? So what are going to be the most cost-effective ways to deploy this bait site? And one of the most frequent questions that comes up is, well, how many bait sites should I have on the landscape? And how is that going to depend on my underlying pig density or my management objective? And then, this potential learned avoidance by individuals who might get excluded at bait and have a sublethal dose, how might that affect my cost effectiveness? So we looked at these questions using a spatially explicit individual-based model. This model included a lot of information about the ecological processes in pig populations, and then the bait uptake process relative to where pigs are on the landscape, and then removal costs that account for distance between bait sites. And the basic idea was we developed this model, we ran simulations, and then we evaluated the output as cost per unit of effectiveness. And our metric for determining cost effectiveness was essentially total cost over the probability of reaching the management objective. And all of the results are summarized in this paper listed down here. And the different objectives we looked at were like an 80% population reduction. So for example, maybe you're trying to manage damage in a population versus a 99% reduction. So you're trying to, really eliminate that population. So for the ecological processes in the model, the way we had this working was we had a gridded landscape of 900 square kilometers, and we looked at different starting densities, so from 1 to 10 pigs per kilometer squared. We accounted for social structure, so the fact that pigs live in sounders, females with their young, and males are independent. We allowed dispersal to happen, natal dispersal, and then also when groups become large, they might break apart and disperse to establish new groups, or females who are on their own might join another group. And we included density-dependent births at a growth rate of the population of 1.4, which is supported by literature. And all of this stuff was happening daily. And then at the start of when we wanted to initialize the toxicant deployment in this simulated population, we would then place bait sites on the landscape according to some density to look into how that density impacted the outcome. And we varied the density in terms of like pigs per bait site from 2 to 130. And this was equivalent to essentially like 1.5 to 0.023 bait sites per kilometer squared. So a realistic range. And then for the baiting process, there are two main components that come into a baiting process. So essentially the probability that a pig finds and eats a bait, and then given that they find and eat that bait, the probability that they die. And these two processes have been looked into in the literature by Nathan Snow and his co-authors. So we use data from these two studies, one looking at the probability that pigs find and consume bait given the distance that they're located from a bait site, and then from pen studies, the proportion of pigs that die given that they eat bait. And for that, we just used a fixed number of 93% that was reported in this study. Now, the baiting process is fairly complex, and we accounted for all this complexity in the model. So basically trying to describe how a manager would go out on the landscape and bait. So essentially what you would do to initialize is you initialize at bait sites at 1.2 times the target bait site density that we used as a parameter in the model. And this is kind of like a scoping period. So you put the bait on the landscape, and this is without the bait box, and you do this for 5 days. And then you select, based on your camera data, you select the 80% of sites that are getting the most visitation. And then you put the box out on the landscape with bait so that those pigs can then be trained to use the box. And then you're still looking at your camera data, and given that you're seeing good usage of the box, you then apply the toxic bait, and you do that for 1 day. And then you go to placebo for 2 days. And if there are no visits after that, so for example, maybe you killed all the pigs, then you would move that bait station somewhere else. But you would repeat this cycle up to a maximum of about 3 times if you are still getting visitation after those days that you put the toxic bait out. And this hasn't been done yet because there hasn't been a need to go more than 1 day, but the model needs to have an upper maximum in case more pigs are still visiting, and it's possible that this could happen in other contexts. And then, if there are still grid cells on the landscape with pigs, you're going to go through this process again. But if you're not getting any visitation based on your camera data, then you're going to tear down bait stations. And so your bait station density is going to decrease over time based on your camera data. So this is how we describe these processes in the model. And then we also had removal costs in the model. And these were from 2 categories. So there's an initial cost for equipment. So let's say you want to go out there on the landscape and really hammer it with a whole bunch of different bait sites. Then you're going to have a higher initial cost because you're going to pay for more boxes up front. And then there's also going to be the daily costs. So there's going to be costs for setting up and removing a bait box, because that's a slightly different cost than if you're actually just monitoring that bait site. And then you've got your daily salary and supply costs for monitoring a non-toxic bait site and then for a toxic bait site. And for each of these, we tallied up the daily costs. And so we have the cost for one bait site and then the total bait sites. And then we also factored in a pairwise distance between bait sites, because it's going to be more expensive to monitor bait sites that are further apart than ones that are closer together on average. So basic assumptions in our removal costs were that cost increases with distance between sites and increases as density decreases. So there's this implicit assumption that it's going to get harder and harder to find pigs as their density decreases. And so costs will increase because you're going to be moving the bait sites around further, more and more, to find more pigs. So now moving into some results. This plot here is showing you, so along the x-axis here, this is the bait station density, so in pigs per bait station. So for example, if you're going so many bait sites that you have like 2 pigs per bait site, all the way up to like 130 pigs per bait site. And this is equivalent, if you want to think in different metrics, on this end of the axis, it's equivalent to like 1.5 bait sites per kilometer squared. Or if you think in terms of like bait sites per kilometer squared, so 1 bait site per 0.67 kilometers squared. So these are just sort of different ways of thinking about the same thing. And then on the y-axis, we have the probability of achieving the objective. And we have 3 different objectives here. Recalling that our study site is 900 square kilometers, and we allow the simulation to run for up to 5 years. And so what we're looking at is whether you're going to reduce your population by 99%, 95%, or 80% within that 5-year period. And we have a density here of 3 pigs per kilometer squared. And so we can see that pretty quickly, if you're shooting for near elimination, pretty quickly you're not able to achieve the objective within 5 years if you start using a not very dense deployment of bait sites. Whereas if you're only shooting for 80% reduction, you can reach your objective pretty consistently across a range of different bait site densities. And then this plot here just gives you an idea of how long that will take according to the different bait site densities. So here, if you're shooting for 99% elimination, so these circles also, they correspond to the proportion that actually eliminate. So here you can see down around 40 pigs per bait station, you're not reaching elimination. And so there's like no circle up here. And the line is just stopping. So, and then this is the 5-year mark where we stop the simulation. Now looking at, so same x-axis here, but now we're looking at the cost per unit of effectiveness for these 3 different objectives you might have. And what we can see is that the optimal bait site density heavily depends on this reduction objective you're shooting for. So you can use a much less dense bait site design and be more cost effective if you're shooting for an 80% reduction versus if you're shooting for a 99% reduction. Then you have to use a super densely placed bait site design. And then this shows you the results as a function of pig density. So here we have the same x-axis, and we're still looking at cost per unit of effectiveness. But each of these lines is for a different starting pig density. And in this particular case, we're targeting like near elimination, 99% reduction. And so what you can see here is that the bottom line cost effectiveness is best at intermediate to low pig density. So if you're going to use just a toxicant for near elimination, you're going to be most cost effective at intermediate pig densities. As you start to get to lower pig densities, the bottom line cost effectiveness is not as good. And same thing for higher densities. And then a second result is that at low pig density, bait sites have to be densely placed. So like this is similar to what we saw on the previous slide. So you can, if you have low pig density, you can only do well if you have super densely placed bait sites. Otherwise, you're not going to be cost effective. And then here are some results for the effects of pig density under these other management objectives. So we still see that bottom line cost effectiveness is worse in low density populations, even when your target reduction or management objective is more on the damage management level rather than elimination. And then also that at higher densities, your bait sites can be placed over a range of pigs per bait site, so a range of different bait densities to optimize cost effectiveness. So you have more flexibility in your bait site design when your pig densities are higher. But again, we see this same result that at intermediate pig density, you're going to maximize your cost effectiveness if you use only a toxicant. And then, so for the last question we looked into was this relationship of how cost effective you are. So that's demonstrated by the colors, given the proportion of pigs that show avoidance behavior after they receive a non-lethal dose. So like here, down here, this would be like, oh, after a pig receives, 10% of pigs will avoid the bait permanently after they receive a non-lethal dose, whereas here 100% of pigs would do that. And then this axis shows you given the proportion that die given consumption. So this is like the bait efficacy. And like I said, we use 0.93 because that's what has been found in pen trials. And what this shows is, with your management objective of 99% reduction, so if you're only using a toxicant and avoidance behavior is really prevalent, then this tool might not be very cost effective. However, so far, what's been observed in pen studies is that avoidance behavior is more on this end. So it might be that, this isn't a super bad feature for this system. However, these observations haven't been made in nature, so the verdict is still out there. Then another result, so like if we look at the same relationship with different objectives, we can see that the effects of avoidance are minor if we apply the toxicant alone for objectives like damage control, like a lower percent of the population reduction as opposed to elimination. And that's under the assumption that 93% would die. But these plots give you sort of the full scope of how these variables relate. So some implications are that we need to consider the management objective. So, how you design the bait site density is heavily affected by what your management objective is. So you're going to be most cost effective. If you're shooting for a 99% reduction near elimination, you're going to be most cost effective if you really put a lot of, increase your bait site density, up to like 1 bait station per 1.7 kilometers or even more dense than that. But if you're only shooting for like an 80% reduction, then you can get away with 1 bait station per 10 kilometers squared to be most cost effective. And then we saw at low pig densities, you need higher bait site densities. So if you're going to be cost effective in the low density populations, regardless of what your objective is, you have to have real densely placed bait sites. And then you'll be most cost effective. This tool in general will be most cost effective to use as a big initial knockdown, but it becomes much less cost effective if it's used alone to reach near elimination. And avoidance could prevent achievement of elimination objectives. But more research is needed in order to measure what proportion of individuals might actually avoid. And so some outstanding questions are, would a mixed strategy be most effective for elimination? And what would be the most cost-effective mix of strategies at low pig density? So we saw that the tool alone might not be cost-effective at low pig densities, but no tool is super cost-effective at low pig densities. It's always hard to get pigs at low pig densities. And so it would be useful to compare the cost effectiveness of this tool at low pig densities relative to others and see if which mix of strategies could be best. And then also we didn't look at how immigration from surrounding populations affects cost effectiveness. So essentially, like some of the strategies that allowed a lower bait site density were still cost effective, but they actually take longer to eliminate the population. And so like if immigration is happening, it could be that those pigs are contributing to damage. And so maybe those wouldn't be so cost effective if you're allowing immigration. And then similarly, we didn't factor in damage costs. And this is a similar concept where like if a strategy takes longer and pigs are allowed on the landscape to be causing more damage, and let's say that damage increases exponentially with pigs left on the landscape, then those strategies that take longer might not be as cost effective. And so like I just like to make a plug for That's exactly why we need to really understand the density damage relationship to plan our most cost-effective strategies. And that concept is laid out really nicely in this paper down here. And that's everything I have to talk about. I'd like to thank my collaborators that are all part of the feral swine group led by VerCauteren here and Nate Snow. And everyone that's helped collect all these data that, have been helping to develop the toxicant and provide parameters for being able to look into how, it could be delivered optimally. That's it.